Usually when you think about a medical treatment, there's this expectation of mechanical precision, you know?
Oh, absolutely. Like, you have a problem, a doctor applies a fix, and that fix works the exact same way every single time.
Right. It's a comforting idea, honestly. Treating the human body like like a car engine where parts can just be swapped out or patched up. But when you step into the world of regenerative medicine,
Oh, that illusion shatters entirely.
it really does. Because specifically in the microscopic environment of human tissue, you aren't dealing with static parts.
No, not at all. You're dealing with living, reactive cells, and they change their entire behavior based on, the specific chemical signals they get from their environment.
Which brings us to this stack of research sitting in front of us today for you, our listener. We're pulling from a pretty massive collection of clinical studies, systematic reviews, and deep biochemical analyses covering regenerative medicine, cytokine release kinetics, and urology.
It's a dense stack today.
It is. But our mission for this deep dive is to look at one of the most popular therapies out there right now, which is platelet-rich plasma, or PRP.
Right, the process where you take a patient's blood, spin it down in a centrifuge, and isolate this golden liquid of concentrated platelets.
Exactly. And then you inject it back into the body to heal damaged tissue. But here's the mind-blowing part that the surface level noise just completely misses. Taking the blood and spinning it down is literally just the preamble.
It's just getting the ingredients ready.
Yeah, because how you wake those platelets up, like how you actually activate them, completely dictates whether they heal the tissue or just destroy themselves in the process.
And we're going to examine this through a highly targeted application, which is injecting PRP into the periurethral space.
Right, so the area immediately surrounding the urethra.
Exactly. We're looking at the stark microscopic differences between two specific ways of activating that PRP. So on one side, you have exogenous activation in a lab using a chemical called calcium gluconate. And then on the other side, you have endogenous activation, which is relying on the body's own native tissue and thrombin to do the work.
But I mean, before we can understand how to activate the medicine, we really need to understand the battlefield we're deploying it into, right?
Yeah. The context is key here.
Yeah.
We're talking about the periurethral space, specifically in the context of treating stress urinary incontinence, or SUI.
Which is a massive quality of life issue for millions of women. It's where physical stress, like coughing, sneezing, laughing,
Ring, yeah.
right, it causes involuntary urine leakage.
Because the underlying issue with SUI is often a failure of urethral coaptation.
Coaptation meaning?
It's the medical term for the urethra's ability to seal, completely shut, under pressure. The tissue of the urethral sphincter complex, it loses its structural integrity, it loses its elasticity, its muscle tone.
And traditionally, the frontline, minimally invasive treatment for this has been injecting synthetic bulking agents into that space, which, based on the literature, is basically just biological putty.
That's a pretty good way to describe it, yeah.
The doctor injects this synthetic material around the urethra to artificially plump up the tissue. It creates a physical volume effect that just forces the urethra shut.
It's a purely mechanical fix.
Yeah, it's like having a door with rusting hinges and a rotting frame that won't stay closed, so you just, shove a wooden wedge under it.
Right, and the wedge forced the door shut for a while.
Yeah.
But it does absolutely nothing to stop the wood from rotting.
Exactly.
Because those bulking agents don't address the underlying tissue degeneration, their effects are often transient. I mean, the material degrades or it shifts, the incontinence returns, and then the patient requires repeated injections over time.
And this is where PRP changes the entire paradigm, because PRP is an autologous biological therapy.
Meaning it's derived from your own blood.
Right. So instead of shoving a synthetic wedge under the door, injecting PRP is supposed to be like hiring a crew of master carpenters to actually rebuild the hinges, reinforce the door frame, and, restore the structure.
And those carpenters are the growth factors packed inside the platelets.
Let's talk about those tools. What are they actually bringing to the periurethral space?
Well, you have PDGF, which is platelet-derived growth factor. Think of PDGF as the site manager. Its primary job is to recruit other cells, like fibroblasts, to migrate into the damaged area.
Okay, so it calls in the workers.
Exactly. Then you have TGF-beta, transforming growth factor beta. Once the fibroblasts arrive, TGF-beta directs them to synthesize new type I and type 3 collagen.
Rebuilding the connective tissue's strength.
You got it. And you can't have a construction site without supply lines, right?
Right. You need materials, blood flow.
Exactly, which is where VEGF comes in, vascular endothelial growth factor. The research notes that VEGF drives angiogenesis. It's essentially engineering entirely new blood vessels to bring oxygen and metabolic support to the newly forming tissue.
That's incredible. And there's even emerging evidence in these urology papers suggesting these factors combined can stimulate myogenic differentiation, meaning they help regenerate the actual neuromuscular tissue of the sphincter.
Which is the holy grail for SUI treatment.
Right. So we have this golden liquid full of these master carpenters. But here's where it gets really interesting. When they're sitting in the syringe, they're completely dormant.
They're asleep, yeah.
They haven't released their growth factors yet. We have to hit a chemical switch to deploy them. And according to the sources, the first major method for hitting that switch is to actually, well, do nothing at all to the PRP before you inject it.
Yeah, that's known as endogenous activation. You take the native sleeping PRP and inject it directly into the periurethral space.
So you're relying entirely on the microscopic environment of the patient's own tissue to wake the platelets up, in situ, right there on site.
Exactly.
But if we aren't adding any chemicals in a lab, what is physically triggering them to wake up in the body?
It comes down to what's already present in the extracellular matrix of that urethral tissue.
Yeah.
So the native environment contains endogenous thrombin, which is the body's natural clotting enzyme.
Okay, that makes sense.
But more surprisingly, and several of these biochemical studies highlight this, the most potent natural activator is actually type I collagen.
Wait, really? Collagen?
Yeah. When the dormant platelets physically bump into the native type I collagen fibers in the tissue, it triggers a physiological cascade that causes them to degranulate and release their payloads.
Letting the tissue itself pull the trigger seems, I don't know, incredibly elegant. But beyond just being a natural process, there has to be a specific biochemical advantage to this, right? I'm guessing it has to do with the pacing of how those growth factors are released.
You're exactly right. The pacing is the entire point.
Mm-hmm.
And it revolves around a concept called receptor oversaturation.
Right.
What's fascinating here is that when you allow the body's native collagen to activate the platelets endogenously, it mimics a natural physiological healing rhythm. So the platelets release their growth factors in a sustained, gradual, perfectly timed pattern.
Because the surrounding cells in the urethra aren't just like soaking up these chemicals like a sponge. They have specific receptors, right?
Right.
Like microscopic catcher's mitts that have to individually catch and process these growth factor molecules.
That is the perfect way to visualize it. If those platelets release their growth factors naturally, they're tossing the balls at a speed the catchers can actually handle.
Okay.
The receptors process the signal, they trigger the cellular repair mechanisms, and then they reset for the next molecule. But if you were to force all the platelets to degranulate instantly in a massive flood...
You're suddenly throwing 1,000 balls at a single catcher.
Exactly. The receptors become completely oversaturated.
Then just get overwhelmed.
Yeah. A fraction of the growth factors are successfully caught and utilized, but the vast majority of that incredible healing potential is essentially wasted. It just gets washed away by the body's fluid dynamics before the cells can even process it.
It's like steeping a tea bag naturally in a mug of hot water.
Yeah.
If you just let it sit there, the flavors and nutrients release at a steady physiological pace that the water can actually absorb. You get a perfect cup of tea.
Right.
But if you take a spoon, smash the tea bag against the side of the mug, and violently tear it open all at once, you end up with a bitter, sludgy mess.
Yeah, that's exactly it. Endogenous activation prevents that bitter sludge. It respects the biological speed limit of the tissue's receptors.
Okay, I follow the logic there, but I have to play devil's advocate for a second.
Go for it.
If native collagen is this brilliant natural activator that perfectly paces the release and prevents receptor oversaturation, why would a clinician ever want to override that beautiful system? Like, why take the PRP into a lab and add chemical activators before the injection? Why mess with the tea bag at all?
That's a great question. And the clinical answer comes down to physical structure.
Structure.
Yeah. Sometimes the goal isn't solely about releasing chemical signals to the cells. It's about physically holding those signals in place in a highly dynamic environment.
Because the periurethral space is subject to constant mechanical movement.
Exactly. Movement, pressure changes, fluid flow. If you inject a liquid, even a perfectly paced natural liquid, a significant portion of it might simply migrate away from the target sphincter before it can do its job.
So you need to build a physical matrix. You need to turn that liquid into something that stays put.
Precisely. When you activate PRP externally, which is called exogenous activation, you're doing more than just waking up the platelets. You're actively triggering the conversion of a protein in the plasma, called fibrinogen, into a dense fiber network.
You're fundamentally altering the physical state of the medicine from a liquid into a three-dimensional gel.
You're building a biological net.
Wow. Okay.
And that net serves two crucial purposes. First, it provides a temporary three-dimensional scaffold. The fibroblasts and endothelial cells, they need a physical structure to crawl across while they proliferate and migrate into the wound space.
And second,
Second, that physical fibrin mesh acts as a protective shield. The tissue is full of proteolytic enzymes, right? Enzymes that break down proteins. The gel locks the bioactive factors inside, shielding them from being degraded too quickly by those enzymes. It holds the medicine exactly where the doctor placed it.
which makes a ton of sense for treating urinary incontinence.
Yeah.
You really want those regenerative materials anchored tightly to the failing sphincter.
Exactly.
And that brings us to the specific chemical the literature prefers for building this net, which is 10% calcium gluconate. How does calcium gluconate actually build this structure?
So calcium gluconate acts as what the biochemists term a slow activator. When it's introduced to the PRP in the lab, it slowly initiates the clotting cascade.
Okay.
The physical result of this slow burn is a highly distinct platelet-rich gel, or PRG. And the defining characteristic of a calcium gluconate gel is that it retracts very slowly.
Retraction meaning how the clot shrinks over time as the fibrin fibers pull together, right?
Right.
So if it's shrinking slowly, I'm guessing that means it maintains its surface area longer. It stays anchored to the surrounding tissue rather than pulling away into a tight little knot.
Yes, exactly. The slow retraction is highly beneficial for barrier properties and tissue adhesion. You want that scaffold to remain expansive and deeply integrated with the damaged urethral sphincter for as long as possible, while the native cells migrate in to do their repair work.
Because a fast-shrinking clot would literally pull itself away from the very tissue it's supposed to be healing.
Yeah, which defeats the purpose entirely.
Okay, so mechanically, calcium gluconate gives us a superior, long-lasting scaffold. But does changing the activation method alter the actual chemical payloads the platelets are releasing? Like, do they still act the same?
Oh, significantly. It shifts quite a bit.
Yeah.
The biochemical analyses in our stack, they utilized electron microscopes and nanoparticle tracking to observe these calcium gluconate clots.
And what did they see?
Well, what they found is that under this slow activation, the platelets largely maintain their structural integrity. You can actually look inside them and still see intact alpha granules. But their chemical output shifts. They release an exceptionally high content of basic fibroblast growth factor, or BFGF.
Which plays a massive role in tissue remodeling and cell proliferation.
It does. But perhaps the most profound shift is that calcium gluconate activation results in a massively high concentration of microvesicles and exosomes being released into the gel.
Wait, exosomes, those aren't just raw proteins, right? They're actual membrane-bound packets.
Yeah, think of exosomes as sophisticated microscopic flash drives.
Flash drives.
Yeah, they're tiny bubbles filled with complex signaling molecules, messenger RNA, and microRNA. So instead of just dumping raw chemicals into the fluid, the platelets use these exosomes to send highly targeted genetic instructions to the surrounding cells.
That's wild. So it coordinates a much more complex healing response.
Exactly.
So calcium gluconate is essentially this elegant, slow burn switch. It builds a sprawling, slow shrinking physical net. It keeps the platelets structurally safe, and it prompts them to send out these sophisticated genetic flash drives.
Yes.
And I noticed the sources specifically emphasized using calcium gluconate over a much more common lab chemical, which is calcium chloride.
Oh, that distinction is vital for urological applications. Calcium chloride is frequently used in general PRP protocols, but it has a major drawback. It tends to produce gross salt deposition.
Meaning what, exactly?
It essentially leaves behind hard, crystalline calcium precipitates inside the tissue after the gel breaks down.
Ouch. Which sounds like leaving microscopic gravel behind in a highly sensitive mucosal tissue like the urethra.
Right. It could cause irritation or inflammation, which completely defeats the purpose of regenerative therapy.
Yeah, you don't want gravel in your sphincter.
Definitely not. Calcium gluconate avoids that almost entirely. It creates a much cleaner, higher quality biological scaffold without the risk of leaving those damaging salt precipitates behind.
Okay, so to really grasp why the researchers are so fascinated by the slow, elegant burn of calcium gluconate, we have to look at the other extreme.
We do.
A significant portion of the literature contrasts calcium gluconate with the other major external activator, exogenous thrombin, specifically bovine or cow-derived thrombin.
Right. If calcium gluconate is a carefully controlled, slow-burning fire that warms a house, bovine thrombin is like dropping a bomb down the chimney.
Whoa.
Yeah. Exogenous thrombin is the most powerful known agonist for platelets. It is the rapid-fire switch.
Based on what we just discussed about wanting a slow shrinking gel, I'm assuming dropping a powerful bomb into the PRP causes a structural problem right out of the gate.
Oh, it does. The physical gel it creates retracts incredibly fast. It pulls together rapidly, shrinking away from the surrounding tissue, which severely limits its ability to act as an integrated scaffold.
But the real horror story happens on a microscopic cellular level, doesn't it?
It's pretty grim. The chemical profile of a thrombin-activated clot is totally different. It does not produce high levels of exosomes or BFGF. Instead, it forcefully ejects a massive spike of PDGF-BB.
Which goes right back to our receptor oversaturation problem. It's throwing 1,000 balls at the catchers all at once, just wasting the medicine. But the research papers describing this went way beyond just wasted medicine. They monitored the thrombin generation curve in the lab, and they found this bizarre two-peaked curve.
Right, and that dual-peaked curve is literally the fingerprint of cellular trauma. The first peak is generated by plasma phospholipids and the initial release of the platelet's own alpha granules.
Okay.
But the second massive peak of thrombin generation is mediated by something called phosphatidylserine.
Wait, I'm going to need you to unpack phosphodilyl what, because that sounds like some heavy biochemistry.
Phosphatidylserine, it's a type of lipid, a fat molecule.
Okay.
In a healthy, happy cell, it's located strictly on the inner leaflet of the cell membrane, the side facing the inside of the cell. But when a cell is subjected to extreme stress or is actively dying, that lipid physically flips to the outer layer of the membrane.
Oh, wow.
Yeah. When phosphatidylserine appears on the outside of a platelet, it acts as a massive red distress flag to the rest of the body, and it exponentially accelerates the clotting cascade.
So that second peak means the exogenous thrombin is hitting the platelets so violently that their cellular membranes are literally flipping inside out in distress.
Yes. The paper published in Hematologica observed this using fluorescent confocal microscopy in real time, and they use a very specific phrase, fatal dysfunction and disintegration of the platelets.
Fatal dysfunction.
The high concentration of bovine thrombin literally pushes the platelets to the point of catastrophic self-destruction.
So the medicine is killing itself before it can heal the patient. How exactly does thrombin force them to self-destruct like that?
Well, it triggers apoptotic pathways, which is programmed cell death. Inside the platelet, there's a dormant executioner protein called procaspase-3.
An executioner protein.
Yeah, and the thrombin activation is so harsh that it cleaves or cuts this protein, waking the executioner up.
Yikes.
Once awake, procaspase-3 initiates the breakdown of the cell, and on top of that, thrombin spikes the activity of calpains.
And what do calpains do in this context?
Think of calpains as microscopic scissors. When they become hyperactive, they start indiscriminately cutting up the platelet's internal cytoskeleton. They're shredding its structural support.
Because the structure is just collapsing.
Exactly.
Yeah.
And while all this internal damage is happening, the massive activation signal forces the cell to consume all of its ATP, its cellular fuel.
So, okay, to put it all together for you listening, you're hitting these incredible little healing cells with bovine thrombin. The thrombin wakes up their internal executioner protein, unleashes microscopic scissors to shred their skeleton, and entirely drains their fuel tank.
Pretty much.
You're forcing the platelets to sprint so unbelievably hard that they physically explode and disintegrate into useless fragments.
And that is the microscopic reality captured on transmission electron microscopes. Unlike the calcium gluconate group, where the platelets were intact and peacefully releasing exosomes, the thrombin group's platelets were completely fragmented. Plus, add in the fact that bovine thrombin is an animal-derived product, which introduces severe clinical risks like immune system, hypersensitivity, uncontrolled bleeding, and thrombosis.
You can really see why the biochemistry heavily favors the calcium gluconate switch.
Absolutely.
The microbiology paints an incredibly clear picture here. We have a clear villain in exogenous thrombin. It nukes the platelets, ruins the physical scaffold, and risks immune responses.
Yep.
And we have two compelling heroes. We have endogenous activation, which relies on native tissue collagen to perfectly pace the release of growth factors without oversaturating the receptors. And we have calcium gluconate, which carefully constructs a clean, salt-free biological net loaded with genetic communication exosomes.
The mechanisms are undeniably elegant.
They really are.
Yeah.
But this leads to the ultimate question for anyone listening to this deep dive who might actually be dealing with stress, urinary incontinence right now.
Okay.
If a doctor opts for the calcium gluconate switch, using it to build this beautiful, slow-shrinking physical scaffold around the urethra, does the literature confirm that it cures the incontinence faster, stronger, or more permanently than other methods?
And this is where we have to take a hard step back from the microscope and ground ourselves firmly in clinical reality.
Okay, lay it on me.
The biomedical literature is incredibly clear on a specific caveat regarding these mechanisms. You cannot make that clinical leap yet.
Really? Even with transmission electron microscopes showing us that one method destroys the cells and the other keeps them alive?
Even then, the biochemistry proves that calcium gluconate safely alters the timing of the growth factor release and creates a vastly superior physical scaffold compared to exogenous thrombin. However, this biological mechanism must be described very cautiously in a clinical setting.
Meaning you can't guarantee results.
Right. You cannot, ethically or scientifically, use this laboratory difference to promise a patient that they will absolutely experience faster, stronger, or more predictable urinary function outcomes.
Because what happens in a pristine petri dish doesn't always cleanly translate to the messy, dynamic reality of the human body.
Precisely. The underlying biology provides a phenomenal, scientifically sound rationale for why a calcium gluconate PRP gel should help restore the urethral sphincter. But the large-scale, long-term, randomized, double-blind clinical trials tracking actual patient outcomes, they're still catching up to the microscopic science.
So the application is still finding its footing.
Yeah. As of right now, utilizing PRP for urological conditions remains largely an investigational or off-label treatment.
That is such a crucial reality check. The microbiology is leaps and bounds ahead of the macroclinical data. But even keeping that caveat in mind, understanding these chemical switches fundamentally changes how we view regenerative medicine, don't you think?
Oh, completely. It forces us to respect the complexity of a living therapy.
It shatters the idea of a standard mechanical fix. PRP isn't just some magical golden potion that you pull off a shelf and inject. It's a highly variable biological material. And its behavior in the periurethral space depends entirely on the chemical switch you use to turn it on. You have the natural, steady pull of the tissue's own collagen, perfectly pacing the release like steeping tea.
Beautifully paced.
You have the slow, structural, scaffold-building reaction of calcium gluconate, pumping out genetic flash drives while holding the medicine in place. And then you have the destructive, rapid burnout of exogenous thrombin, just shredding the cells from the inside out.
And it is all the exact same starting material, just dictated by a different switch.
It's mind-blowing.
You know, if we pull back and connect this microscopic mechanism to the broader landscape of medicine, it leaves us with a truly provocative thought for you to consider.
Oh, where are you going with this?
Well, think about the vast history of clinical trials and medical research.
Okay.
If simply changing the activator from thrombin to calcium gluconate can transform PRP from a quick-burst liquid of dyeing fragmented cells into a slow-release structural gel loaded with sophisticated microvesicles.
Right.
How many other failed or inconsistent medical treatments out there in the literature aren't actually bad treatments at all?
Oh, wow. That is wild.
Right. How many promising biological therapies have we discarded or labeled ineffective simply because we're using the wrong biological switch to turn them on?
That is an incredible thought to end on. It proves that in human biology, the how is infinitely more important than the what. We aren't just swapping out engine parts. We are slowly learning how to speak the body's deeply complex language. Thank you for joining us on this deep dive into the hidden mechanics of regenerative medicine. Keep questioning the science, keep looking past the surface, and we will catch you on the next one.